So, welcome everybody to another Institute seminar day seminar. Uh, and we welcome Roohani Sharma, who's going to talk about reusing algorithms under conflict free constraints. Uh, Welcome, Roohani.
Thank you for the invitation. So, yes, as Sushmita said, the talk is primarily about seeing whether we can reuse algorithms when we are encountered with some additional constraints, and particularly the constraints of conflict freeness will be of utmost importance to us. So, let me begin by showing you this. So this is pretty much the kind of problem that we want to deal with in this talk in our own very little way. So typically, this is a problem that typically every algorithm designer faces. So a client comes up with a problem, and the algorithm designer spends days or years or sometimes even decades to try to come up with an algorithm that solves the problem. And then almost when the designer is ready with the solution, the client modifies the problem at hand. And this is probably unavoidable because the demands are growing with time. So this is something that's not really in our control. But what we are interested in is the following. So let's say as an algorithm designer, I design an algorithm to solve a problem, and now a client comes up with a constraint that does not really require, that doesn't really change the problem at hand, but requires us to solve a problem with an additional property. So what we're interested in is the following. So suppose I have a solution that solves a particular problem, and then suddenly when someone asks me to give a solution to a problem with certain additional property, ideally we would want that our efforts scale up in proportion to the additional property that is required. So in an ideal world, we would want that since the extra condition is only an additive condition, we would want to be able to reuse what we have already developed for the original problem at hand, and then probably do some additional work to cater to the additional constraint that the client has put on us. And typically, more often than not, this is not the case. So the effort does not really scale up to the additive constraints. And in this talk, we're going to design some tool that allows us to reuse the work already done for a particular problem when an additional constraint comes into picture. And for the rest of the talk, I'm going to start with a problem, and throughout the talk, we'll try to design some good algorithm for the problem, and it's only towards the end of the talk that I'll talk about this reusability paradigm. So when we're trying to solve this problem, we'll design some tools, and we'll see how these tools can be used in general to reuse algorithms when they are encountered with certain kinds of constraints. So now let me just start with a problem, and we'll see how to solve this problem throughout the talk. And the problem is sort of motivated by current events. So this is a problem that I call the virus control problem. So imagine in a not so hypothetical world right now, we have a set of countries marked by these fictional flags. And there is a country which is marked by a virus. So let's say there is this country which is infected by a virus. We call this the spreader country. And then there is a country tagged fragile. So this is the country that is very fragile and cannot risk getting a virus. And other countries are more or less immune to the virus at hand. So this is the model that we have, and and our goal is to prevent the fragile country from getting the virus, from being infected by the virus. And the way the virus spreads in our model is the following. Suppose this country has the virus, and if this country allows travel to, let's say, this green country, and allowing travel is represented by putting a line between these two countries. If the country maroon, the spreader country, allows travel to this country green, then since the maroon country had the virus, we assume that if this travel is allowed, the green country also gets the virus. And so this is how the virus propagates. And one is not allowed to travel between every pair of countries, which is typically the case. So the countries which allow the pair of countries which allow travel to and from between them, they are represented by these edge relations. So if I put an arc between two countries, it means travel is allowed to and fro these countries. And these relations are called edge relations. And typically such a structure which contains objects and a binary relation defining them in the form of these edges, such structures are called graphs. So this is the model that we have. The model of the transport or the communication is represented by these edges. And we discussed how the virus spreads. And the goal is to prevent the fragile country from getting the virus. And the way the fragile country can get the virus is, for example, since the spreader has the virus, we take this edge, fly to this country, and this gets the virus, and then we fly to this yellow country, and this gets the virus, and then we fly to the fragile country, and this gets the virus. So now, as a common consensus, all the countries decide to protect the fragile country from getting the virus, and they decide on following the following protocol. They decide on closing down borders of certain number of countries, such that once all the borders for these specified set of countries is closed, the virus cannot reach the fragile country. And because we want to do it in an economical way, we want to close borders of a minimum number of vertices, such that once I close the borders of those vertices, the virus cannot reach the fragile country. For example, in this case, if I close the borders of the countries marked with cross, it's not difficult to see that the virus cannot reach the fragile vertex, because if I close borders for these countries, so when I say close borders, I mean we close all inbound and outbound flights to and from these countries. So when we close these borders, these countries just disappear together with their connections, and now it's easy to see that if the virus is here, the virus can spread only to these countries and will never reach a fragile country. So this is the problem at hand that we want to discuss. So in the next slide, let me just define the abstract model that captures this problem. So this problem is captured by a very classical problem in graph theory called the SG separator problem. So in this problem, the input is a graph G, and there are two vertices S and T. And the goal is to decide to find out the minimum number of vertices that can be deleted from the graph, such that it's not possible to reach T from S. So for example, in this graph, if I delete these three vertices, there is no way that I can reach T from S. And this is a classical and a fundamental problem in graph theory, and its solutions were known as early as early 50s, 1950s. And one solves this problem via the concept of flows. So there is a celebrated result that associates the minimum SG separators in a graph with maximum SG flows in the graph. So a celebrated theorem says that a min cut or a min separator between a pair of vertices is actually equal to the max flow that can be routed between these two vertices. And just to quickly and informally define what a flow between two vertices is. So imagine that S vertex is a producer. There is a factory that produces something, and T is the consumer. And S wants to route, and these edges represent some pipelines via which the products will be routed, and each pipeline has a capacity. In our case, each pipeline or the edge has capacity 1. And the goal is to decide how many units of the produce can be routed from the producer S to the consumer T under the following conditions. So the conditions are that at no point do we congest the edges. So if the pipeline has unit capacity, at no point do we send more than unit produce along this pipeline. And then the second property is that there is no congestion happening. So, or in other words, these vertices do not have any storage capacity. So if, let's say, 1 unit of product is routed through this pipeline, this unit product should come out of these edges that are emanating out of these vertices. So this is very informally what the notion of an ST flow is. And as for example, in this example, if you see, if I route 1 unit of product through the yellow path and 1 unit of product through the green path and 1 unit of product through the pink path, the two conditions of no congestion and not having to store produce at vertices is satisfied. And in fact, in this example, it can be shown that only 3 units of product can indeed be routed in this graph. And as I said before, the celebrated theorem says that if one is able to find out what is the maximum amount of product that can be routed in this graph, that amount is equal to the minimum size of the ST separator. And so the ST separator problem basically boils down to finding max ST flows in the graph. And that can be done with sort of greedy-ish algorithms. I'll not go into the details of this. And this can be done quite efficiently. And in particular, this can be done in time, which is proportional to the number of edges. E represents the number of edges in the graph. And F is the maximum possible flow that can be routed in the graph. And I'll later talk about why I call these efficient algorithms or why such kind of algorithms are good to us. But the moral of this slide is that the ST problem has solutions via flows. And now the idea of associating flows with ST separators is a very elegant idea. And now this is the problem at hand. And now let's try and add some more constraints in the problem. And let's see if we can use the same ideas to solve this constraint problem. In particular, I begin by adding this constraint of outliers to the ST separator problem. So if I have to motivate this problem, let's go back to the virus control scenario. So there we assume that all the countries unanimously agreed to help the fragile country, and all the countries unanimously agreed that, okay, if we are asked to close our borders, we will close our borders, if that's the case. But in an ideal situation, that might not really be the case. There are always some outliers in any universe. So in particular, suppose a set of countries do not want to participate in the protocol. They really don't care about what happens to the fragile country, and they are not ready to close their borders. And that's where this problem comes into picture. So this problem is defined as follows. So the input is the same as the previous problem, but now we also have a set of outliers, which is the set of vertices X. And now the goal is to delete a minimum number of vertices that are non-outliers. So now we're not allowed to delete the outlier vertices because they refuse to participate in saving the fragile district. So we can only delete the non-outlier vertices such that after their removal, the same thing happens. You cannot reach T from S. So this is an added constraint, and we would want to be able to solve this problem using the ideas developed for the ST separator problem. And in fact, in this case, we are indeed lucky. For this special kind of constraint, the outlier constraint, we can indeed reuse the algorithm of the ST separator problem. And let me try to give you an intuition of why one can do that. So suppose in this figure, the green vertex is an outlier. So in this figure, I've just drawn one outlier vertex just to convey the idea. So this is an outlier. This vertex does not want to participate in saving the fragile district. In other words, it does not want to close its border, or it does not want to get deleted. But this vertex still provides connectivity between vertices, and or in other words, this vertex still can propagate the virus. So we just need to keep the information that these vertices can propagate the viruses, and in which ways can it propagate the viruses. As long as we can keep this information, we can forget about these outlier vertices completely. And there's an easy way to do it. For example, so look at the neighbors of this green vertex. So between any two, between any two neighbors, for example, look at this neighbor and this neighbor, these two neighbors can be reached via the green vertex. So in other words, if the virus has reached this vertex, then it can reach this vertex via the green outlier vertex. And we just need to remember that the virus can reach from here to here, in which case we just put an edge between these two vertices. So for any pair of neighbors of the green vertices, we actually go and put an edge signifying that these two vertices can be reached via a green vertex, and then at the end we completely forget about green vertex. Note that by doing so, we have captured the information required to see how the virus can propagate. And since now we have deleted the outlier vertex completely, we can actually go and solve the SC separator problem on this graph. So for these kind of constraints, we can indeed reuse the algorithms that we have already set up for the SC separator problem. So we got lucky here. So let us remember that adding outliers is easy for us. It does not make the problem harder. We can reuse algorithms here because we're going to use it later during the talk. So now let me talk about adding other kind of constraint, which is the constraint of conflicts. So in this constraint, so to motivate this scenario, consider the following situation. Suppose now we decide on a set of vertices which needs to, or we decide on a set of countries whose borders need to be closed, and now once these countries are decided, we leave it on these countries to unanimously come up with a protocol of closing the borders. And to be able to do this process peacefully, we would want that these countries do not have conflicting opinions or do not have conflicts with each other. This problem can be modeled as follows. So we have this graph with black edges, which was the same as the previous graph. Now, additionally, we also have these kind of conflict edges. So we have these pink edges representing conflict between two vertices. So if two countries have a conflict between them, we add this pink edge between them. And now we want a set of vertices such that in the black graph, when I delete the set of vertices, those vertices disconnect S from T. And in the pink graph, none of these vertices should have an edge between them. So for example, in this case, this red crossed solution is not a solution because there is a pink edge connecting these two red vertices. But this green solution is a conflict-free solution because there is no pink edge connecting these green crossed vertices. So now we want such solutions, and it turns out that finding such solutions becomes extremely hard. So before that, just a formal definition of the problem would be, one can imagine as being given two graphs. One is the black graph, which is the connectivity graph, and one is the pink graph, which is the conflict graph on the same set of vertices. And the goal is to delete a minimum number of vertices such that whose removal in the black graph disconnects S from T, and which in the pink graph have no pink edge between them. And as I said before, forget reusing the ST separator problem, ST separator algorithm for this problem. Even the ideas of flows do not seem to work to give solutions for this problem. And there's a fundamental reason why this happens, and the reason being the following. So P and NP complete are the holy grail of complexity classes in CS. So very informally speaking, P is the class of problems that which have algorithms whose running time is a polynomial function of the input size. Whereas for NP complete problems, we do not expect such algorithms unless something very unimaginable happens. And but for these problems, there is a polynomial time algorithm which can always verify a proposed solution. So having these two classes, what really happens here is that the ST separator problem and the ST separator with outlier problems lies in the P class, whereas the ST separator without conflicts problem lies in the NP class. So we don't expect a very good algorithm for this problem. In fact, forget about the ST separator constraint. Just asking for a maximum size is also NP complete. So now, just to motivate why we are so scared of this NP complete class. So we don't expect are algorithms whose dependence on the input is polynomial for these problems. In particular, for example, it's easy to see that these problems have an algorithm which has a running time of the form 2 power v, which corresponds to the algorithm that goes and check every possible subset of vertices and checks if this is indeed a solution, and this can be done in polynomial time. So just to highlight what changes so significantly when we go from polynomial time algorithms to exponential time algorithms, let's consider some concrete values and see how those running times behaves on those concrete values. For example, assume that we had a graph 1000 vertices. So an algorithm that takes 2 power v times takes roughly around 10 power 300 instructions, and my quick Google search showed that the fastest supercomputer at present solves roughly 10 to the power 17 instructions per second. This means to solve these 10 power 300 instructions, one will take roughly 10 to the power 227 years, which is insane. And just a fun fact, the age of the earth is merely 10 to the power 10 years. So let us compare this with the algorithm that we had for the ST separator problem. So again, on the same sized input, this problem takes a microsecond to run on the fastest computer and roughly a second on your nicely configured MacBook Pro. So that's why having exponential time algorithms for problems is something that's highly undesirable, because the running times blew up even for very small values of input, which is like 1000 in this case. So now, if this is the scenario, let's see what we can do to circumvent NP completeness. So one thing that one can do is that one can add the notion of budgets. Typically, when we are seeking for solutions, very rarely are we interested in finding minimum size or maximum size solutions. Typically, we have a budget at hand, and all we're interested in is whether the solution fits our budget. For example, in the ST separator problem, let's say we also have a budget K, and we're interested in seeing if we can delete at most K vertices, which disconnects S from T. And with this problem at hand, one can improve the previous exponential running time slightly and make an algorithm of running time which amounts to checking all k-size subsets of the vertex to find out if they form a solution. And this definitely is going to be this algorithm, but it will take some 10 million years on the fastest supercomputer. So just introducing the budget is not enough, and this is where we introduce the notion of fixed parameter tractability. And the notion of fixed parameter tractability is the following. For NP-complete problems, typically for NP-complete problems, in the realm of fixed parameter tractability, we analyze the running times of our algorithm on 2 clocks. So we analyze the running time of the algorithm. We analyze the dependence on the input of input on running.
You should try and finish in the next few minutes, so that we're aware of your time, the time. Sorry for the interruption.
So typically we're interested in running times, which depends exponentially on K probably, but only polynomially on the input size. So for example, some nice running times of this form would be this, which is linear in the input and to an exponential function of K. And for example, if you compare this kind of an algorithm with a 2 power K kind of an algorithm, this takes just a microsecond on the fastest computer. So now we're interested in designing fixed parameter tractable algorithms for this ST separator problem. And as it turns out that both these problems cannot be FPT unless again something bad happens. But what we can still show is that, so I'll be interested in the thing mark start. What we can still show is that the problem is tractable or is FPT when the config graph is planar or degenerate. So just to motivate the problem a little, planar graphs are graphs which can be drawn without the edges crossing each other, which can be drawn on a sheet. And these graphs are interesting because these graphs model the world map with borders. So if you have vertices representing the countries of the map and edges representing the relation saying that these countries share a border, then planar graphs can nicely capture these graphs. And And hence, even if we allow our conflict graph to be a planar graph, this still captures a lot of problems, because a lot of times conflicts happens with neighboring countries. So this is still a good enough result. And I'll just briefly tell what we can say about these kind of results. So planar, maybe just quickly. So planar graphs are graphs. A nice thing about planar graphs is that they are graphs which have a vertex of degree at most 5. And because every subgraph of a planar graph is planar, every subgraph of a planar graph has degree 5. Such graphs are called 5D degenerate. And what we show, let me skip this. What we show is that when the conflict graph is restricted to be a D-degenerate graph, the problem can be solved in FPT time. And the way we do it is the following. So this is the most crucial tool that we have. So we compute a family of conflict-free sets in the conflict graph with the following property, that if you look at any at most case size conflict-free set in the conflict graph, there exists some set in the family that contains it. So the family might not contain all conflict-free sets of the conflict graph, but they definitely contain enough sets such that any case size conflict-free set is contained in this graph. And we call this family a K conflict-free covering family. And note that once we have this family, there is a very easy algorithm for the problem, which does the following. It computes a K conflict-free covering family for the conflict graph. And now for each set X in the family, it solves the ST separator problem with outliers, where the outlier set is the vertex set minus X. Because we know that any conflict-free set is contained in some set of the family, so for every set X, we check if there is a solution lying inside the set. So what happens here is that we have traded off the conflict-free constraints with the outlier constraints, and these constraints are much easier to tackle. And hence, for this problem, now we can reuse the algorithm of the ST separator problem with outliers here. And so, having said that, just one last caveat is that we want to be able to compute this family in a nice time and of a nice size. And this is our main result. This is our main tool that says that if the graph is D-degenerate, then such a family can be of this size. This size, note, this is a size where the exponential dependence of the size is only in K and the degeneracy. It can be computed in the family of this size can be computed for D-degenerate graphs, and it can be computed in times proportional to the size. So this is our main result, and the proof of it is very elegant, but I'll skip the proof that we have. So using this result, we can actually reuse the algorithm for SC separators with outliers to design an algorithm for SC separator with outliers. So now just one last comment about how we can use this tool to reuse algorithms for for other problems. So you can think of a conflict-free version of your favorite problem, and then compute a K covering family, conflict-free covering family for the conflict graph, and then for each set in the family, you solve your favorite problem with the outliers constraint corresponding to this set. And typically, as I said before, outlier constraints are easier to handle than the conflict-free constraints, and this tool allows us to trade the difficult things for the easier things. So using this tool, one can design problems, design conflict-free versions of various problems, and by reusing algorithms of the respective problems. But I'll skip defining these problems. And just the last slide. So this notion of conflict-freeness can be generalized for nowhere dense graphs. So right now we showed that there is a nice family for D-degenerate graphs. This can be generalized for something called nowhere dense graphs. And then I'll skip the defining all these things, but then there are natural barriers on trying to generalize the notion of conflict-freeness, especially for these notions marked in red. And there are, of course, a lot of scope of seeing what other kind of constraints can be captured by the kind of tools that we had. So this is all that I had to say, and thank you for your attention.
Thanks, Roohani. Yes, Vani has a question, and I'm afraid we may not have time for more than one question. So, Vani, go ahead.
Roohani, thanks. It was a very nice talk. I think I understood at least a little bit. But I have a very general question about this. You started in the introduction that this question of asking, can you reuse an algorithm if additional constraints are put? Is there a theoretical way of knowing what should be the nature of this additional constraint put such that you can determine whether the algorithm can be used or not? Is there a way, a priori way to know this? Eh,
I would say no, because typically I think that is what I wanted to convey in my very first slide. Typically, when an algorithm designer is problem, one tries to problem in very ad hoc ways, and depending on what ad hoc ways are used to design the problem, those define. I mean, it's only in retrospect that we can go over these ad hoc ways and try to realize, okay, that maybe adding this constraint will not affect these ad hoc ways, and so on. So as long as the process of algorithm design remains ad hoc, I don't think there's an a priori way of dealing with it. But having said that, there is a fair amount of meta theorems right now. So there is a fair amount of theorems that try to design algorithms for a large class of problems uniformly, like in a very systematic way. So for those kind of results, maybe you can, but typically, if the whole design procedure is ad hoc, one cannot.
okay, all right, thank you.
So, thanks again, Roohani, for your talk.